Sì.
Okay. Good morning to everybody. Today we should discuss, for completing our presentation of fluid, perfect fluid equations in Eulerian description, we must introduce the concept of material derivatives. And if you don't use the right mathematical framework, this concept can become very obscure. And actually, I did inquire about every student in fluid mechanics I met in every engineering school, and I discovered that only few of them had understood that what we are doing usually in solid mechanics and what we are doing in fluid mechanics are simply a description of motion either here in the space of positions or there in the space of Lagrangian space of material particles. So I want to, so in a sense, we must discuss in bigger detail about the Eulerian description of motion and to the Lagrangian description of motion. Okay. So let us start considering the placement key. So the placement key, as we said many times, map the position of a material particle into the label, therefore the position in the reference configuration of a material particle into the actual position of this material particle. So key of xp and t, now time plays a role, is equal to small xp. So this is the label of the material particle. And this is the position occupied by P. The material particle P, and this is the position occupied by P. So when you block a material particle, so let us block this material particle and assume that time is flowing. So what you have in a time interval, the position of this material particle changes. So you have xp, the same, always the same xp, and this is key at instant t. Then you have key at instant tau, and then finally key of t plus delta t. Tau belongs to the time interval t plus delta t. Okay, and you have the trajectory. This is the trajectory of capital XP or P. Okay, if you confuse the label with the material particle. So if you calculate the partial time derivative of key of x and t, and you calculate this at any instant t0, okay, what you have? You have a vector which is this is Lagrangian, and this is Eulerian description. You have a vector which is the tangent vector to the trajectory of x, capital XP. Okay, but remark, this is the vector of the material particle XP. Okay, and in different times, the XP is the same, but its position is different, and the velocity v, this we can call v of capital X and t, is relative to another position. Okay, so v of capital X and t is the velocity associated to capital X at instant t. And this has this definition has a precise physical meaning. Now, remark that the domain, this is a very strange field in a sense, because its domain is a point in the Lagrangian description, and its domain is the set of displacements in the Eulerian description. Okay, so it is rather difficult to draw this field, because you cannot draw it here, because this is not a displacement in the Eulerian space. Okay, and you cannot draw here because this is a position. It is not a material point. Okay, so Euler, understanding this problem, defined what the Eulerian velocity field by the way, we have already done this for rigid body motion, but let us define it in a more general setting. How? I consider the placement. I calculate for x the velocity of x. And then, instead of considering x as an independent variable, we consider small x as independent variable. So what we do, we write v of small x and t as v of k minus 1 x t. So we take a position. X is a position. Then we can consider k minus 1, the inverse of placement. So we start with x, which is a position. Okay. Then we find remark, at instant t, the material particle which occupies small x at instant t. Erden, please, at least you switch on the video. So this complicated sentence is written with this simple formula. Sorry, I need small x. So when I say the material particle which occupies at instant x at instant t, I mean this material particle. The inverse of placement applied to x and t. Okay? And we glue v at x. Okay, so this velocity, this arrow here, is the velocity relative to the material particle which is passing there in a certain instant. Okay? Okay. So we have defined a, so we have defined an Eulerian field starting from a vector field, an Eulerian vector field, defined in C star via key minus 1. Okay, so it is essential, remark, for doing this, it is essential that key is 1 to 1. If you remember, when we started discussing the basic kinematical assumptions, we said we are inventing a mathematical model in which 2 points cannot shrink to occupy, two material particles, xp1 and xp2, cannot shrink to occupy a single point, a single position. Okay. Of course, you can have mechanical situations where this is happening, but you know, mathematically speaking, we are limiting our analysis to the case where every material particle occupies, in the reference configuration, occupies a distinct position in space, so that the inverse key minus 1 is defined. Okay, so remember this, we cannot introduce the Eulerian velocity field as we did here without having the inverse function there. Okay. Now, let us stop a little bit in this discussion and let us consider a purely Eulerian description of motion. And this is good a fluid. So what we have as kinematical descriptors. So let us think what we have introduced. We have introduced rho of small x and t. You remember, we defined the mass, volumic mass density, the in Eulerian description. Okay. Of course, we in background, you know, what is very strange, you know, in the books of fluid mechanics, what is very strange is that, okay, maybe we can use a graphic, nice graphic, you know, we use this, you know, this, I hope you can see this lighter drawing. You know, in the background, you always have the Lagrangian description, but in fluid mechanics, you have the tendency to forget about it. So what we say is that rho star of capital X dV star, which is the mass in the small volume in the reference configuration, is equal to rho small x, where small x corresponds to capital X, dV. The mass, this is the mass in Lagrangian description, and this is the same mass in Eulerian description. Okay? Now, as we know that dV is determinant of F dV star, okay? So, we have a relationship between rho star and rho x, okay? So, knowing key and its gradient and the determinant of its gradient, we have defined the field rho small x t t. Okay? So knowing the placement of our continuum, you can define the Eulerian field dense volumic mass density in the Eulerian description. Then, in every point, you can define V of x and t, which is the velocity field which we have just defined. So let us remark another remark. There is a unique placement behind ρ and V. So if you remember, ρ that F is equal to ρ star, okay? And that F is that grad key. So ρ is related to the gradient of key. The velocity V, capital X and T, is equal to d key over dt, capital X blocked. So in a sense, key is primitive for ρ and V. In other words, if you have a motion, if you have a motion, so if the function key exists, then ρ and V cannot be independent. And we must now find the relationship between ρ and V, which is a consequence of the existence of placement. Okay. Now, the existence of placement together with the conservation of mass is what we will exploit. So now let us consider a channel. Okay. Where our fluid is flowing. Actually, this formula is true also for a solid. So this is useful in the mechanics of fluids, but it is true also in the mechanics of solids. And actually, what we will try to write is a relationship between the field V of X and T, okay, and the field ρ of small x and t. So what you do, you choose what is called a fixed Eulerian control volume. So you choose a volume V and you block this Eulerian volume. Then you define the mass inside V at instant t. and you define this as integral over the volume, remark, not time dependent, of rho of x t in the volume. This is the mass inside V at instant t. Okay? Then the flux of mass outcoming the boundary of V. At the boundary of V, you have that there is a normal n. You have in every point of the boundary of V, you have the velocity V of x and t. Okay? And I hope you remember that V dot n times rho is the mass outcome from V. In this small area of the boundary through the boundary V. Okay, so the flux of mass outcoming V is integral over the boundary of V of rho V dot n, the area. Okay, so the variation of the total mass is equal to minus the outcoming flow of mass, the area, the volume, so this is the area. Okay, so if I am extracting, when the mass is coming out, because you have chosen n pointing outwards, when the mass is coming out, you have a decrease of the mass inside the volume V. Okay. Now, mathematically speaking, you should know that when the integration domain does not depend on a variable, the partial derivative can go inside. So this is equal. This is not true always. If V is varying, then you have troubles. But as V is blocked, you can allow the partial derivative to come in. So you have that this integral is equal to this other integral. And then on the other side, you can apply to rho V the Gauss theorem. The surface volume, the flux, is actually equal to the divergence of rho V integrated in the volume. Okay? So, for every volume, control volume, you have that the integral over V of d rho over dt plus divergence of rho V dV is equal to 0. if you use the difficult localization argument needed then you get in that for every x belonging to your channel, so let's say C, the actual configuration, d rho over dt plus div rho v is equal to 0. And this is the Eulerian version of balance of mass. It establishes a relationship between rho and v. And I will give you probably some exercises, some hints on how using this definition and this relationship for getting it directly, simply using the the relationship between derivatives, changing the order of derivatives, because in a sense here you have what? You have the time derivative of rho, which depends on the gradient of k, and here you have the divergence, so the space derivative of v, which depends on time derivative with respect to k. So the basic fundamental reason for which this equation is true is that the order of derivation with respect different variables can be changed. Okay. Of course, if you have a bone and inside this volume you have a process of growth, then you will get a source term here, which is called the production of mass. Okay. But this is a complicated argument. We will try eventually to discuss at the end of this course, if somebody is interested. What I want to say is that, of course, no mass production is another accepted hypothesis. Okay. Now, we need to understand always if we have the Eulerian description, what happens to so-called, how to define and how to calculate the so-called material derivative of an Eulerian field. So this is something which is relevant. So let us consider always, we cannot forget the reference configuration in this context. So we have a tensor field whatsoever. Let's call it phi of x, small x, and t. So I have in the Eulerian description, this is the Lagrangian description. In the Eulerian description, I have defined a generic field, f of x and t. I can calculate d phi over dt, small x fixed, and I can calculate d phi over d small x, t fixed. What this, sometimes we can write this grad small x phi. These are equivalent notations. Okay. If you want to write component-wise, you write d phi over dxi, t fixed. Okay. So what are these partial derivatives? I have blocked a time instant t, and I see how this field is varying, changing the variable small x. In this case, I get this is the Eulerian gradient. Okay, Eulerian gradient. Okay. Otherwise, I can block small x, so I stay in one position and I let time flowing. So I estimate phi at x blocked in different time instants. Okay? And I calculate this partial derivative. Now, we could need to make something else. We could need to consider phi. Okay, maybe it is better if I use small phi as it is Eulerian. So I try to keep the notation. Okay, what I could do, I could consider phi of key of capital X t t. And this is what we could call phi Eulerian as a capital X and t dependent. So what I do, I choose one material particle, capital X. I go in the Eulerian configuration via key. Okay. Then I am in a position, small x. I estimate my Eulerian field in small x and t. Okay. And in this way, I define phi Lagrangian, sorry, in this way. So you understand, telling this with words without using the formalism of composed functions can be a nightmare. So I can tell you in a very elegant way that phi Lagrangian of capital X and T is the evaluation of the Eulerian field in the subsequent positions occupied by one and the same material particle. Actually, in the ancient books, you find this. Lagrange wrote something like that. But this definition in words is rather difficult to catch, to grasp, until you write this equation. So you have an Eulerian field. You have defined it in the Eulerian description, in every position and time. Then you have your motion, okay? And you estimate the field in the Lagrangian description. How? The corresponding field phi Lagrangian is equal to the phi Eulerian calculated in the position occupied by capital X at instant t at instant t. Okay? So we define material derivative of phi, the derivative of the time material derivative, the derivative of phi L with respect to time, the partial derivative with respect to time. This is the definition. So I am writing a material particle and I check how the phis which are met by this material particle are changing in time. Okay? So Erden, your face is a big question mark. Do you have any comment or not?
No, I'm familiar with this stuff. It's okay.
So you will tell me. So maybe you are asking yourself why I'm telling these things. Obvious. Huh? Okay. So in Berkeley they are doing this in this way, right?
Similar, yeah. I mean,
for example,
for mass balance, right?
Yeah.
Yeah. We did the same thing, yeah.
Okay. So you know the tradition in Berkeley is not so bad at the end. By the way, America has the force of recovering. You have seen at the end, they sent Trump away. So we'll see how he will resist. But, you know, America is very good in many aspects. Okay. So let us calculate this derivative. So we have d over dt. You understand that this symbol is meaningless if you don't say what is blocked. Okay, so d over dt with capital X block of phi L x t, and we calculate this trivially using the theorem of derivative of composed functions. So you have d over dt of with small x blocked phi plus d over d small x of phi t blocked, and we must derive d key over dt. Okay. By the way, imagine if I had written this equation. As you can find in many books. You know, it's better if I cross immediately wrong equations, which I write, because in the past, some student told me, you wrote it. So I immediately crossed it. You know, this abuse of notation, confusing phi L with phi, cannot be accepted. Otherwise, this formula is clearly meaningless. In order to reinforce the point, I wrote that capital X is blocked and small x is blocked there. Okay, so to make, and I even changed the name of the function as it should be. Okay, now remark that we have that d over dt of at x blocked phi L of x t. This is a field. So on the right-hand side, we should have a Lagrangian field. And indeed, we have d over dt small x blocked of phi, okay, but calculated when in chi of x, key of xt, t, t. Okay, so we calculate the partial derivative at x blocked, we get a function of small x and t, but as we started with definition, the chain rule tells me that this function, this partial derivative, must be evaluated in key of capital X, t, and t. Plus, once more, we have d phi over dx blocked t, calculated in key of x, t, and t, dot d key over dt. I have no space, but here the variable are capital X and t. So this is the first version of the calculation concerning the time material derivative. However, we need it in the Eulerian description. So instead of evaluating this in capital X, we want to evaluate it in small x. So what we do? We do d over dt capital X of phi L. Instead of capital X, we write key minus 1 small x t, comma t. So this becomes an Eulerian field. And this is our material derivative. This is equal to what? Now, if I calculate this, you know, if I have key of key minus 1 of x t, this is equal to x by definition of the inverse. So when I calculate the left-hand side in key minus 1 and x and t, this becomes small x. So you have d phi over dt in small x, function of small x and t, plus, similarly, d phi over dx t blocked, calculated in small x and t, dot, here we have the Eulerian velocity field, which we defined before. And this is also an Eulerian field. So if you have phi and you want to calculate its rate of variation, is time rate of variation, following a material particle, okay, then you must use the definition this one. This definition has the physical meaning which we have in mind. Why? Because phi lambda of capital X and T is equal to phi calculated in key of capital X T T. So when time is varying, you are riding a fixed X and you estimate phi along the trajectory. This is the trajectory of capital X. So this is the position of capital X at instant t. This is key of capital X tau, and this is key capital X t plus delta t. Okay, you estimate at instant t phi of key of X t comma t, and at instant t plus tau plus delta t, and you estimate this increment to calculate the rate we are dealing with. As a consequence, and you learn by heart this magic formula whose meaning we have discussed in full detail, d over dt of phi, this is an Eulerian derivative, so you don't write phi lambda composed key minus 1, okay? D over dt of phi is equal to the partial time derivative of phi plus the Eulerian gradient of phi dot the velocity. And this is a definition whose meaning I hope I managed to explain you in detail. You understand that without the chain rule for derivatives and the concept of composed function, all these becomes a nightmare. Okay, I want to spend some words about this. For many years, I was teaching to engineers studying environmental engineering. And they came to me very often declaring that all these concepts, I was teaching together with a colleague, professor of geometry. So we had an integrated course where I was explaining the fundamental ideas of tensor calculus and tensor algebra together with the colleague of geometry. So in order to help the colleagues in hydraulics, we were teaching this mathematics, because this is mathematics. So which is the standard objection of environmental engineers? The standard objection is, this is mathematics, nothing to do with practical engineering. Okay. However, they wanted to study the diffusion of pollutant inside a porous matrix. How can you study this without the balance of mass I was discussing you? I was showing you, you have the mass of pollutants in a control volume V, and you have the flow of the pollutants through the boundary of the control volume V, and you have how the concentration of pollutants is changing when flow is transporting them. I mean, you cannot even formulate these concepts without the mathematics I'm describing now. Moreover, if you have a chemical reaction occurring in the pollutants, the material derivative of the mass concentration of pollutants is changing in time because of the chemical reaction which is occurring. So the language of engineering science is this kind of mathematics. By the way, this is a rephrasing of Galileo's statement about physics. Okay. I really cannot understand how it is possible that colleagues of hydraulics may manage to give this definition without a word of explanation. It is something which comes out of the blue, and they don't explain the reason for which this definition is given. Now, we have some time, so we can proceed using these concepts. The first application is acceleration field in the Eulerian description. If you remember, we wrote minus grad P, Eulerian grad, equal external Eulerian volume forces minus mass density times acceleration. Okay, so I am here in one point. I have a small volume control. I write Eulerian balance of forces, if you remember what we said yesterday. And we say, as we know that forces are causing accelerations, inertial forces, okay, then we have that a term involving acceleration must appear in the integral expression representing balance of force. So we need to define in every point small x the acceleration of the material particle which at instant t finds in small x. So remember, if the velocity, if key of capital X and t is derived one time with respect to time having capital X blocked, you have the Lagrangian velocity. If you derive another time with respect to time having capital X blocked, key of capital X and t, then you have the acceleration in the Lagrangian description. What is a small x and t? This is, by definition, a. So the a Eulerian is the a Lagrangian calculated in chi minus 1 of small x, t, and t. So the acceleration field which we need in this balance equation is exactly the material derivative of the Eulerian velocity field v, x, and t. V, x, and t has been defined as v key minus 1 capital X t, t. Or if you want, v Lagrangian of capital X and t is equal to v Eulerian calculated in key capital X t, t. The acceleration, Eulerian acceleration, is the material derivative of v Eulerian of x and t. Okay, So if we write this equation, then we write P as a function of constitutive function of rho. And we write d rho over dt plus div rho v equals 0. This set of equations should characterize the fields rho and v. However, we have a difficulty because we have everywhere only rho and v except in this acceleration. Okay, but the acceleration is equal to d over dt of the velocity plus grad v Eulerian dot v, because of our reasoning. So the whole set can be written in this way, the whole set of equations, minus grad p equal externally applied volume forces minus rho times dv over dt plus grad xv dot v. Then you write p as a function of rho, and then you write balance of mass and this is a set of partial differential equations. Of course, you must add boundary conditions to these partial differential equations. The existence and uniqueness theorem for this problem has been formulated by the Italian school. Let me proud of the fact that, usually Italians tend to hate other Italians. We are inheriting this Greek attitude to ignore the other Italians. Okay. However, this problem has been studied by Lagrange, Piola, then Beltrami, and then continued until Graffi, who has proven the existence and uniqueness for boundary condition problems for this system of partial differential equations with the modern formalism of Sobolev. So we know when this problem can be well posed. I will try to tell you this in the next minutes. So this problem can be the basis of the study of flowing of some fluids. Okay, maybe in the minutes we are left, I can give you an idea of the boundary conditions to be added for having well-posedness. So Graffi proved that let us divide the boundary in two parts. three parts. One part is where no outcoming flow is applied. So the part where Vn is 0. These are the walls. Then you have where V dot n is the external normal of the boundaries of our channel. I call it channel because everything is Eulerian. Okay, so let us consider the part of the boundary where V dot n is negative. So if this is the velocity on the boundary, we have the incoming flow. Okay, and then you have here, for instance, the outcoming flow. V dot n is positive, so you have outcoming flow. Okay, so you give the velocity everywhere in the boundary of your channel. Somewhere the normal velocity is 0. You must give the normal velocity only. This is important. Then somewhere you have incoming flow. So this is given, Vn of x given. And also you have the outcoming flow, which is given. Okay? In order to have uniqueness, existence and uniqueness of the problem, represented by these boundary conditions and these partial differential equations, you must specify ρ in the incoming flow boundary. Okay? And this has a very clear physical interpretation. You must tell to your mathematical problem how much mass is entering in every point where incoming flow is arriving. On the other side, if you have a part of the boundary where you have assigned the outcoming flow, there the mass density is given by the evolution equations, the partial differential equations inside the body. And this information is very important if you want to try to solve some mechanics of fluids problems. For instance, using COMSOL. The knowledge of right boundary conditions is essential. Okay. Maybe we can do what I promised at the beginning of the previous lecture, that is considering the case of incompressible fluids as a particular case of equations. By the way, the mathematical treatment of this limit is due to Lagrange and requires to be done in a clear way the concept of Lagrange multipliers. But following Erden's suggestion, we will deal with this mathematical tool later. My idea is that we should rest a little bit playing with COMSOL, and then when you will see how powerful COMSOL is, only then you will go back to the mathematical foundations of what we are doing with a stronger motivation. Okay. Okay. Now look at this equation. It is worth that we repeat the reasoning. Now I am not using Lagrange multipliers, so Erden will forgive me if my treatment is not rigorous, but I don't believe that in Berkeley they are using Lagrange multipliers for incompressibility constraint. Are they doing it or not?
Yes, we introduced Lagrange multiplier. We discussed about this.
Ah, very well. So you already know this.
Yeah, yeah.
So we will do this with everybody soon. So you will be able, Erden, to help me in this. So you will be a little bit upset, but okay. Imagine to have this particular constitutive equation for the pressure. Okay, where alpha is a compressibility or a stiffness factor. Okay, so when this alpha tends to plus infinity, okay, of course, the pressure must remain bounded, because if you have infinite pressures, then you will be able to move masses with infinite force, right? And this is against every principle of thermodynamics. So this must tend to zero in such a way that the product remains finite. Okay? But you know that 0 times infinity is not determined, in the sense that every real number can be a limit of the form 0 times infinity. So when we impose we get incompressibility means alpha tending to plus infinity. Okay. This implies P finite and rho equal to rho 0. Finite and unknown. Okay. So what happens to our equations? This becomes meaningless. This becomes rho 0. Okay. P remains unknown to be determined using the first equation. D rho over dt is 0. Rho is constant, gets out of the divergence, and we are left with what? We are left with minus grad P equal BV minus rho acceleration, and the acceleration we know is given in terms of the velocity, and div velocity equals 0. So the fields, the unknown fields, become rho 0 is given, become and V, rho is equal to a constant rho 0. Okay? And this equation has been written by Lagrange. Okay, this fluid mechanics is very important when you want to study aqueducts, water pipes. Many problems, many phenomena can be described by this nice theory. I will try to find a nice proof of the famous D'Alembert paradox. Imagine to have a wing and to have a fluid flow around the wing. Okay, everybody experienced this fact that the wing is experiencing a resultant force exerted by the fluid flowing around it, and this force is the force which allows airplanes to fly and allows birds to fly. However, if you calculate integral over the boundary of the wing, okay, of P n, which is the resultant force applied to the wing by the fluid, you get 0. Using these equations, but also using these equations. So you can hear even nowadays people saying that airplanes fly, birds fly, and scientists do not know why. Of course, this is a fake statement. It is a fake news. It is like the fake news that in Pennsylvania, the vote has been, there are tricks in the vote. It is an absolute fake news. Why? The D'Alembert paradox gives us a clear statement. You cannot describe the interaction between a fluid and an obstacle by using the model Euler fluid. That's it. You must invent another more complicated model. We will briefly treat this. This model is called Stokes-Navier fluids. There is a controversy because, you know, British people and French people always quarreled one with the other, trying to decide who is the inventor of something. Okay. Okay, I think that now we can stop. And I think the lecture is ended. If